All right, so as I previewed in the end of the last slide, what I'd like to do is basically plug in our guess for the form of the solution. So, for example, this is ui, so this is the displacement in the ith direction of the kth atom of the lth unit cell. So I would like to plug in essentially F equals ma. So if this is this, so the second derivative with respect to time of this thing times mass, so that's the mass times acceleration, should equal the sum of the forces acting on that. And we showed last time that the sum of those forces was given by basically a summation over all of the different atoms that could be moving. And so that's the displacement of all of the atoms that could be moving times the force that would occur if those things move from their equilibrium positions. And that summation might include the atom that's, or does include the atom that's actually in question. So that's one of the atoms in the summation. So let's just work through that math a little bit more. So you'll see that, for example, the e to the I omega t comes up on both sides. So just like we've seen before, that's going to cancel. Most of the other stuff doesn't really cancel, though, if I'm really sort of critically looking at this. One thing I can do, though, is I can multiply through. So I've got an e to the I qt, where t is a translation vector over here. I've got something kind of similar over here. The only difference is that the thing over here has a subscript L prime. So, the unit cell that is associated with this translation vector isn't necessarily the same as this one. But let me just, I'm going to move that to one side. I'll keep the mass on the other side for the moment. So let me do that. So that's m sub k u, oops, already made a mistake. Let's start over. Okay, so I need to take two derivatives with respect to time. That's going to pop out two factors of minus I omega. So because it pops out two of them, the minus signs cancel with one another, but you have a minus I here, or an I squared that produces a minus I. So that is minus mk omega squared times ui k0 equals minus sign summation over all of the other stuff. This kind of just goes along for the ride for right now. Actually, I'm gonna do a little bit of trickery here. Actually, why don't let me do something here. So cut down on the number of steps we have to actually write out. So what I'm going to do is I'm going to write this as two summations, actually. So this was actually a triple summation. So it's a summation over the k primes, the l primes, and the j primes. I'm just going to explicitly write one of them a little separately than the others. So this is the summation over all of the possible unit vector, or all of the possible unit cells that could be interacting with the atom in question. Okay, so let's do that. So that is phi ij k l k prime l e to the I q dotted with, and I'm going to combine these now. So I've got a TL prime minus the translation vector associated with the lth unit cell. And remember, these things canceled out, but the only thing that's left is this. I haven't really accounted for this thing yet. So that should go, and I'm going to write this, I'm going to box this separately, and then I'm going to write u j k prime 0. So I wrote this in a particular way because it's starting to look a little bit like a matrix equation. So I've got like some set of things that I'm interested in solving for over here, and I've got that over here as a linear factor. The only thing that's different is that the indices here are kind of not exactly the same as the ones over here, right? So these ones were involved in the summation over here. So that's the only thing that's different about this and this, is these were involved in the summation. Well, that's starting to look a lot like a linear algebraic, problem, or a matrix problem. So that's sort of why I broke it up this way. So in principle, after you do the summation over the L's that are all the different possible L primes that are here, this thing is really just a matrix, that involves KL as one set of, IK, and another one that involves the J K prime. Now I'm going to do one other thing. So right now this L that's sitting here is kind of an arbitrary number. We'll do one of two things here. One is I could recognize that since these things are actually lattice vectors, there's really no difference. Like if I think about what this is really saying, it's saying that if I choose L, I need to sum over all of the possible, L being like some unit cell. So let's say L is some particular unit cell, and then I need to do this summation over all the possible unit cells it could interact with. Really all that matters is the difference between the distance of those unit cells. So rather than actually explicitly allowing this to be arbitrary and then summing this over every possible combination, what I could do is I could just say that the value of L, I could just set it to be equal to 0, and then I still have to do this summation over all of the possible different ways of rearranging that. So what I'm going to do is basically I'm not sure if I explicitly really want to write this out again. I could write this whole equation again and just do this, but what I'm going to do is, I'm going to do that. I'm going to do it because I'll do it. Okay, so let me just write this again. But what I'm going to do is I'm going to switch this L to which represented the unit cell that I was, performing this solution on. What I'm going to do is I'm just going to do that in the first unit cell. Or the 0th unit cell, I should say. And I still have to do the summation over all possible unit cells. But what that does is it means that I no longer really have to consider this translation vector, because that translation vector will be 0. So this makes it look a little bit more compact. By the way, I don't necessarily have to do the solution in the 0th unit cell. All that's really true is that since these are really just differences between translation vectors, essentially it turns out to be equivalent to do all those summations in the 0th unit cell. So that's what I'm going to do. Basically, I'm just switching this to a 0 there, and then similarly, I'm switching this to a 0 here. So this thing is really a matrix. This is pretty close to our final result, but I'll show you that there's one additional thing that people typically do. Let's see, do I have enough space to do it here? I do. I'm just going to do it. So an additional trick that people do to make this look a little bit cleaner is they define what's called a mass-reduced displacement as, so what I'll do is I'll just redefine the displacements using a change of variable as mk to the, is it half? I gotta remind myself, half times v in the ith unit, in the ith direction of the kth vector in the lth unit unit cell equals ui k L. So this is just a change of variable. So if I make that change of variable, then this whole problem, what I can do is I can then divide by, so why would you do this? Basically because what happens is, so this thing's going to spit out a thing that looks like, did I get this backwards? This will spit out a factor of MK half. This should be minus half. So what will happen is that this will spit out a factor of mk to the minus half. So that'll turn this into mk to the half. This portion will put out something that looks like mk to the minus half, or mk prime to the minus half. And it'll basically make this equation symmetric. So the two minus signs cancel over here. And so the quote final result is that omega squared VIK0 equals the sum over K prime J times this other summation over L prime of the interatomic force constants divided by mk to the half times mk prime, or mk prime to the half, times this factor of e to the iq dot with the lattice vector times u j k prime u. Okay, so this thing inside this thing, that is called the dynamical matrix, or sometimes just the dynamic matrix. So if I look at what I have, oh, sorry, I wrote U, but I meant V. Okay, so what I have here is something that I'll call the dynamic matrix. It's usually written like this. I'll write it as D, so it's called the dynamic matrix, Dij, K prime, and that thing in principle actually depends on what value of Q you take. But for a given value of Q, basically this thing is a matrix, or you can think about it as a matrix, and in fact it's a symmetric matrix, which is the reason we made this change of variable. So it's symmetric because I can interchange K and K prime and it still forms all the same stuff. Remember that this summation over L happens here, but this summation doesn't involve K, or essentially doesn't involve K or K prime. So this factor doesn't really matter. So what comes out of this after you do that summation is a symmetric matrix called the dynamic matrix. And that dynamic matrix is essentially a matrix that interacts with a term on the other side that turns this into an eigenvalue problem. I'm going to clear all this work off here. So really this last result is the main thing I was looking for. So I'm looking for this thing. This thing here defines an eigenvalue problem that we would like to solve. So for any particular value of Q, or any particular value of wave vector, this thing just becomes a matrix of some values. So for any value of Q, there's some matrix here, and so I have a matrix times a vector equals a constant times a vector. That is an eigenvalue problem for omega. So just like we had before in the one-dimensional case, we set up an eigenvalue problem and we solve that eigenvalue problem to find omega, which will give us a whole bunch of different values of frequency, each associated with a value of Q. That is a dispersion relationship. So what we need to do now is basically think about well, how big is this dynamic matrix? How many values of omega are going to come out for a particular value of Q? So that's what I want to think about next. Let me clear all this work off and we'll talk about that now.